Really nice to be invited here. So today I'm going to talk about some recent advancement in self-improving AI models and some of the challenges. Before we talk about self-improving AI models, I want to first go over what's the standard alignment approach we take in fine-tuning LLMs. So first of all, we're going to start from a user query that could be explain the moon landing to a 6-year-old. And then we're going to fit this user query to LLM, and the LLM might produce several different answers using random sampling. So in this case, we have 4 answers, A, B, C, and D. And then we simply fit in these 4 responses to human, and we let the human to decide what's the ranking over the quality of our responses. So once we have the labeling results, we're going to apply the preference optimization, also known as RLAIF, or reinforcement learning from human feedback, or DPO, direct preference optimization, to improve the model's generation based on feedback. However, a main drawback of this approach is that the human needs to read the responses carefully in order to make any decisions about the quality of the responses. So let's imagine when LLMs is getting better and better, it also becomes harder and harder for human to process all the responses and to provide high quality feedback. So an example of this, if you ask the LLM to generate a really hard code snippet for really hard problems, for example, if the model is really capable and is able to generate the entire MapReduce code in just one click, then because the answer is too long and it's really specific to coding, so it's impossible for an average human to even read all the response and to determine the quality of the response. So this simply means that the RL from human feedback cannot scale if the model is approaching the human intelligence. So this immediately raises really interesting research questions, which is how can we continue to improve the superhuman models? So I'm going to share 2 of my observations why this is possible. So the first one will be the prover-verifier gap. So the prover-verifier gap simply states that for some problems, evaluate a solution is easier than generating one. So there are some examples. For example, if we're asking to solve a puzzle, then, for example, like Sudoku, we're not trained to solve this puzzle, then it might take an average human to solve this puzzle within 30 minutes. But if we're provided with a solution and we tell us the rule about this game, then it's easier for an average human to validate the correctness of our results in just 1 minute. This is also true for math. So for a lot of math problems, if you're asked to prove some theorem, then it's really hard. But if you're provided with a step-by-step solution, then it's much easier for us to verify the correctness. As well as programming, it's hard to come up with a solution that's satisfy the time constraint or some like other clever things to have to be proposed. But if you're provided with a solution, we can simply write down some unit test and then run the code on these unit tests to validate correctness. However, there are also some examples where verification isn't much easier. So a notable example would be information retrieval. So suppose we are facing the questions, what's the capital of Bhutan? Then even if you're provided with a really lengthy explanation of the response, it is also impossible for us to verify its correctness unless we know the results. There's a gap between the prover and verifier is able for us to improve the generation quality, utilize this prover-verifier gap. And the answer is yes. So 2022 paper coming from Anthropic named Constitutional AI Harmlessness from AI Feedback actually took this approach. What they did is they basically handwritten a lot of constitutions that tell us what kind of responses we're looking for. For example, we want the response to be harmless, we want it to be helpful, and we don't want it to contain no information. So after we have the written down constitutions, we are going to first sample some response from the model, and then we give this constitution to the model and ask it to judge whether this this response follow the constitution. And the model might output some critic, which is some detailed thought process of whether this is doing the right job. And we can leverage the feedback and send it back to the LLM and let it to improve the generation, or we can leverage the feedback to select a good and bad response and do preference optimization. So let a work called self-rewarding language model simplify this approach. So basically, the workflow works like this. So we first generate several candidate responses, and then we apply prompting to evaluate each response and assign a score for the responses. And then we'll calculate the average score for each response. And then we basically select the best and worst pair according to the average score. So once we have the good and bad pairs, which is also the chosen and rejected pairs in DPO, we can apply RL to further reinforce the performance of the LLM to encourage it to generate more good response while decreasing the probability to generate the bad responses. The other observation is the self-improving system is actually bottlenecked by the evaluation capability of the model. So this is evidenced by the fact that the past at K is extremely strong for even not very strong LLM if it's provided with large inference budget and a gold verifier. An example of this would be the math dataset. So in this math dataset, it's just basically some math problem provided with a ground truth answer. So we can directly leverage like Python to try to parse the answer from the model's response and then check whether it's aligned with the ground truth answer. In this problem, for a model like Gamma 2B, the solve rate at just one sample is only around 10%. But if you're allowed to sample it from the model a lot of times, like 10,000 times, then nearly 95 of problems can be solved by the model. And this is also true for coding. So for a less capable model like Gamma 7B, the solve at one rate for the coding problem is nearly like 1% or 2%, which is extremely low. But if you allow to sample it for 10,000 times, then there are 20% of the problem can be solved by the model. So this indicates improvement for about 10 times. Another example of this is the paper called Font Search, Mathematical Discoveries from Program Search with Large Language Models. In this paper, the author formulates the problem of trying to find a really good mathematical construction to writing a good heuristic function. And they derive a system to evaluate the quality of the heuristic function. So the only job for the LLM is to try to write a lot of heuristic function and to use the verifier to select the best one. Use a really simple approach, which is they try to divide all of the responses into several groups, and then they apply the evolutional algorithm within each group to improve the quality of the responses. And they also maintain the diversity by maintaining several groups. And after a few time period, they're going to eliminate like half of the groups based on their score. And then they just sample a huge amount of responses. And surprisingly, they're able to find a really good heuristic function that actually leads to a mathematical discovery that no human have found before. And they are not doing this with a really capable model. It's only like maybe like a 13B model, which is not considered really strong. But surprisingly, if it's provided with a large inference budget, it's able to surpass the human expectation with a gold verifier. So, however, in the problem of self-improving, the main bottleneck is we don't have the gold verifier. So this is true for fuzzy tasks where it's hard to define a gold verifier, or it's also true for some extremely hard tasks where it's just simply impossible for human to come up with a gold answer. So this implies that we can make a huge gain if we can try to make the evaluation capability of the model stronger so that it's enough to select the best response among a lot of candidate responses. There are actually a lot of ideas to improve the evaluation capability of the model. So one really notable idea is called the GAN-like approach, because we can, first of all, try to generate some good and bad responses with the labels, and then we can simply train the LLM to try to distinguish the good and bad, and this will make the model better at distinguish the different responses. For example, in this paper called RLCD, the author basically developed two prompt templates. The first one is the harmless template, and the other one is the harmful template. So for every problem, it's going to prompt the model to generate two responses. One is harmless and one is harmful. And they simply label the response coming from the harmless to be 1 and the other to be 0. This is based on the assumption that the response that's coming from the harmless template is going to be better than the response coming from the harmful template. A problem with this approach is that if the response coming from the harmless template and the harmful template are really different, then by simply creating the preference pair doesn't bring extra information for the model to learn, because the model is already really simple to distinguish between two very different responses. But on the other hand, if you control the quality in the response to be smaller by applying some different prompt template, then sometimes the model can ignore your instruction. And sometimes the response coming from a harmless prompt would be even worse than coming from a harmful prompt. So in this case, the label you provided is actually really noisy. So you have to trade off the information that you can learn from the sample as well as like how noisy is the label you get. So this makes the GAN-like approach unfavorable. So another really simple idea is to make use of meta-evaluation. So meta-evaluation basically means the process of examine the evaluation process itself and check whether it followed the evaluation rubric. So however, we are based on the assumption that evaluate the evaluation process according to the rubric is actually easier than coming up with a good evaluation on the fly. So this could be also interpreted as a gap between the meta-evaluation and evaluation. Let's put all the ideas together. So how can we improve the generation and evaluation together? So first of all, we're going to break down this problem into using the LLM itself to create preference pairs for both improving the generation and the evaluation. So for improving the generation, we'll apply the same or similar methods as the self-rewarding paper, where we're going to start from a prompt. In this case, what is machine learning? And then we will prompt the model to generate several responses. One might be like machine learning is a subfield of artificial intelligence, that blah, blah, blah. And then we're going to tell the model, can you assign a score from 0 to 5 to this response based on the following rubrics? And as a result, the answer might look like, first of all, the response is relevant, so I'm going to assign 1 point. And secondly, address a portion of the questions, so I'm going to assign additional point, and blah, blah, blah. And finally, I conclude with, therefore, I would assign 3 out of 5 to this response. So we're going to sample a lot of judgments to the same response so that we are able to average over the final score. And then we're going to simply look at the average score of all the responses, and we select the best response as the one with the highest score and worst response with the one with the lowest score. However, if we simply do this, then there's going to be a large difference between the length of the chosen response and the rejected response, because the model actually favor the more lengthy response. So we additionally apply length control filtering, which is we basically look at the length of the chosen and rejected, and if they're too different, then we discard the pair. So by doing this, we can mitigate this length bias in the LLM as a judge paradigm. So for creating the evaluation dataset, we are going to start from a response, and then we do the same. we will sample a lot of evaluation using the same evaluation template. In this case, the evaluation give a score of 3 out of 5. And then we're gonna tell the model all the relevant information. Like, first of all, what is the questions, and then what is the response, and then we're gonna randomly select two different evaluation process, which we call judgment A and B. And they might contain different thought process, and they might share the same, they might provide the same score finally, but they might also differ in their score. So in this case, the judgment A provide a score of 2, but the B provides 3. So we're going to ask, according to the rubric, which judgment do you think is more appropriate? This will result in a really lengthy comparison, which I hide here. And the final result might be, I think judgment B is more appropriate according to the rubric. If we compare all of the pairs within a same response, then we will essentially result in a battle matrix between all of the evaluation processes. But how can we try to select the best and worst evaluation process using all of the results we have? The idea is really simple. So we can try to leverage logistic regression and the Bradley-Taylor loss to convert the pairwise battle results into an absolute score for each evaluation process, which we termed ALO score. And then we're going to simply select the best and worst evaluation process as the one with the highest ALO score and the lowest ALO score. And same, we're going to apply lens control filtering to make sure the model doesn't exploit the lens bias in the LLMs judge process. And finally, we are going to merge the preference dataset we have created for improving the generation and evaluation. And we simply apply a unified strategy, which is direct preference optimization to improve the model. We have performed the experiment on Llama 3 8B model, and we care about the generation quality, and it's measured by a benchmark called alpaca eval. The orange line is actually the curve provided by co-training the generation quality and the evaluation quality. And the blue line is basically we discard the data set we have created for improving the evaluation, and we only focus on generation. We can see in this curve, the y-axis represents the win rate of the response provided by our model compared with GPT-4. Initially, it started from around 25%, but after 4 iterations, it reached a win rate of around 40% if we co-train both the evaluation and the generation. But if we only train on the generation, then because the evaluation quality doesn't improve much throughout the training, so it's going to saturate earlier and results in a lower win rate. So we're really curious, like, what is the categories that we made the biggest improvement? So we classify all of the prompts of Alpaca Eval 2 into 18 different categories that might include like science, social interaction, and software development, as well as like language learning and mathematics. Surprisingly, we found like almost in all of the categories, the model improved, or at least it doesn't degrade, especially in like problems like science. There's a really huge jump in the win rate. And the only one we lost is the language learning, and which is also reasonable because the model is already pretty strong in language learning. So maybe improve it doesn't work well. So because it's already so good. Okay, so talk about the generation quality. So we are also really interested in whether the model's evaluation capability has also increased throughout the training. What we evaluate this, we basically have a prompt set called Open Assistant. We select a set of the prompts, and then we generate responses for every prompt. And we're going to apply the same self-rewarding process to assign a score for every response. And after we have the scores, we can also apply the chosen and rejected pairs to select the highest score response and the lowest score response. And then we're going to ask a stronger judge, which is GPT-4 as a judge, to see whether the labeling provided by GPT-4 agree with the one we provided. So initially, the agreement between the GPT-4 as a judge and our model is just slightly above random. So it's only around 55%. But after 4 rounds of training, it's largely increased to 64%, which is considered to be okay, because the human internal agreement is only around like 70%. So this indicates that throughout the training, the evaluation capability has also increased. I want to mention that although our method seems really promising, but there is also some limitations. So first of all, I want to say that self-evaluation is really biased. The model would actually favor the longer response, even if it's really bad. So this is also known as the lens bias. So in our case, we actually designed this lens control filtering to specifically address this bias. And the other thing is that the model actually favors its own response. So this is documented in the paper called LLM evaluators recognize and favor their own generation. So we also observed this phenomenon where in the initial iteration, we found that most of the time the LLM would assign a score around 4 to its own response. But after the first round of training, we found the model have shifted its score from purely focusing on 4 to a nearly even distribution around 4 and 4.5 and 5. After the second round of training, the model have learned to concentrate most of its score assignment to around 4.75 and 4.9. So if we continue to use the LLM's self-feedback to train the evaluation capability, then the score is gonna shift more and more closer to 5. And eventually at some point, it's gonna saturate because it's gonna think every response coming from the model would have a score of 5. So it's not gonna be able to use the feedback to improve the generation anymore. And the other thing is the model actually favor the response with prettier style. So this is actually a study come after our paper. So in our paper, we didn't address this kind of bias, but you can check this out. So basically it says that if there's more markdown symbols in the response, like markdown headers, like markdown list, then it's more likely for a human to choose the response as a favorite response. So this is not only true for a human judge, but it's even more true for LLM as a judge, because LLM as a judge is easily distracted with this kind of prettier style thing. And we haven't addressed this. I will mention that there are also some other limitations, like the evaluation can be totally unreliable, or sometimes the model just doesn't have the ability to understand the thinking process if the questions is pretty hard, or it doesn't have the relevant information to decide the correctness. There's so many bias, but these bias has to be addressed. Otherwise, it's gonna result in a saturation in the generation quality, or it's gonna totally collapse the model.
What do you think like of evaluation frameworks, like given from NVIDIA NeMo framework we could use to evaluate responses and run it through multiple loops until it gets it right? Like, what's your general opinion on that? Or is it better to have your own evaluation model?
I think the key point of evaluation is that, so we've been talking a lot about like the inference scaling law, right? As we've been talking about if we can sample a lot of responses and potentially there's going to be a good response. And but the fact that we have neglect is this is also true for an evaluator. So for an evaluator, if you just sample the evaluation for just one time, then it might be a really bad one. But if you sample it for a lot of times, if you're willing to spend more compute, then potentially you can design some sort of framework that can provide a more accurate judgments than simply do it once. So in our paper, we actually sample multiple responses and try to average the score. If the evaluation can contain more information, like if it assign a score in different category, so we can maybe check whether they're correct and how well they agree with each other and use it to provide a more fine-grained signal to select a good and bad response rather than just simply look at the final score. There's definitely a lot of work to be done in designing some sort of system that can rely on multiple calls to the same LLM to improve the accuracy of the evaluation. And this is not only limited to sampling or repeatedly sampling for a lot of time than average, but it will also require the model to learn to use tools to verify the results provided in the response, right? And maybe asking for help if the model doesn't think it has enough knowledge for evaluate this response. Yeah, so in short, I definitely believe that that's a really interesting and plausible way to do the evaluation.
How many judges or of LLMs do you recommend to evaluate the task? Like how many are recommended?
In our experiment, we actually use the same LLM for different roles. So we have three roles. So first of all is the LLM that generate the response, and the LLM that score the response, and then the LLM that score the evaluation. So they're sharing the same weight, but they're using different prompts.
Yeah, I was wondering about this. The accuracy of the models can be improved if you prompt the model to break down their answer into individual steps or logical steps. And I was wondering if you've explored the ability to not only judge the final answer and improve that, but also looking at the responses for each individual step to try to make it easier for the judges to determine the accuracy.
We didn't specifically ask the model to evaluate the response step by step. And the problem is that without prompting and without further training, the LLM is not used to generate a step-by-step solution to the problem. So we definitely have some instruction in the prompt, tell the model to evaluate the response more carefully. But because the model we're using is quite small, so it's sometimes unreliable. Just ignore the instruction and maybe want to directly jump to the final score, and that is hard to control. But I definitely think that first of all, if we're solving some really complex problem, so we have to force the model to write down a really step-by-step answer, and then to ask the judge to evaluate the response step by step. And I definitely believe that this is going to be helpful for like math problems.
Is there like any experiment where models, like where's like a response from another model, not the same model, but a response from another model, and just to see will it continue favoring its own response, or it might choose the response of another model?
Yeah, we actually did this experiment, but it's not in the paper. So as in this paper, the LLM evaluator recognize and favor their own generations. I think they did the experiment to compare I mean, like you can directly ask the GPT-4 model to rank its own response with a Gemini model, and it's definitely gonna prefer its own response. But the things we've observed is that the model tends to assign a really high score for its own response, and sometimes assign a lower score for response that is out of its own distribution.
And maybe it's like speculative question. Like, do you think with the current methods, we're on a good path to AGI, or you think it's something like significantly lacking?
My belief is that if the model gets stronger, then its core capability of evaluating is going to be stronger. So as long as the model can try to break down the thought process into steps that are verifiable, then it will be much and much easier for a stronger model to evaluate its own response.
I think about a lot, all the space of things that we're going to be using AI for. And I think, a large quantity of things we're going to do is actually causal reasoning in various ways. Mathematical reasoning, is very deterministic. Causal reasoning is very multi-step. When you look at all the different problems that arise in life that require you to reason about causality, there's just this exponential number of ways in which causality combines. And for that, I'm very optimistic about inference time compute. I think if you expect to just build larger and larger LLMs that sort of can reason about, those exponential number of combinations, I don't think it's, I think, it's an exponential scaling curve. If they learn specific ones, of course, that happen a lot, they might be able to cache them. So, but I think, inference time has a lot of potential to really cover a much larger space of problems that arise, because that causality nature of things is just so pervasive. And in that case, though, that things are not very deterministic. When you say almost any causal statement you make tends to be, very probabilistic, and it's hard to even nail down, all the factors that allow you to, create a Markov probability, because there's always something else that could contribute. The idea of a judge, is, I don't know, people study the mathematical stuff so much. I'd like to see them maybe study, the more fuzzy probabilistic stuff a bit more in judging. I think that would be useful. When we're looking at the improvement, I'm also thinking these things are going to have to learn more than what we give them, because a lot of like what you've talked about today feels like I'm going to lock myself in a room and think how and try to improve my intelligence, right? But the way these things are going to get smarter than us is they're going to be grounded out in the world in some way. Maybe the judge is accessing, scientific experiments or seeing the results of things in some way. In your case, I guess the one input that is external is that they might be seeing a new stream of prompts, right? That was beyond what they were trained on. But I don't know. Those are some thoughts I had. I'm excited about this stuff. I think this is really neat what you're looking at.
I think it's really insightful that I do believe that if the model is going to surpass human intelligence some way, then it might require at least a small portion of external feedback for it to achieve that efficiently. Because otherwise, if you just been locked in the room and then think the problem, then maybe the only problem you can solve is math, because that only requires you to be locked in the room. But if you want to do some more complicated things, like if you want to explore if there's any new algorithm that nobody can predict whether it's going to be good or bad unless we try it, then it's better that we try it.